In this, my approach was that I started with the get overflow function, overflow list function to identify which cells would overflow. I used a helper function called count underscore neighbors to check each direction around a cell, ensuring only valid neighbors within the grid boundaries are counted. This approach avoided complexity compared to using of the nested loops. I iterated through each cell, counting its neighbors, and compare the cell's value to the number of neighbors. If the cell's value is greater or equal to the number of neighbors, it is added to the overflow list. In the returning list, the function returns the list of the overflow cells if they are found, otherwise it returns none. The overflow function had to be recursive. I used the get overflow list to identify overflowing cells and added type checking to ensure all values are integers. In the initial sign check, I checked if all non-zero cells have same sign to determine if further overflowing processing was needed. If all cells have the same sign, the grid is not overflowing. For the handling overflows, I reset I reset overflowing cells to zero and distributed their values to neighbors, updating signs accordingly. This follows the overflow rules. Then next, I made a deep copy of the modified grid and added it to the queue, then call the function recursively to handle the subsequent overflows, incrementing the count each time. In the base case also, if no further overflows are needed, the function returns zero, stopping the recursion. In conclusion, my approach focused on the modularity and clarity of the code. By breaking down the problem into smaller functions and ensuring through checks, I handled the complexity of the overflow process effectively. One challenge that I faced was that ensuring the recursion terminated correctly, which included the careful handling of base cases and recursive calls. That's it for today. Thank you.